Welcome to Ask and Learn.
In this problem, we have nitrogen in a rigid vessel which is heated, and we wish to calculate the work done and the heat transfer. We assume that nitrogen is an ideal gas, the kinetic and potential energy changes are negligible, and we can use the constant specific heat at room temperature for nitrogen. Now, the constant volume specific heat for nitrogen at room temperature is 0.743 kilojoule per kg Kelvin. So now, we will take the nitrogen as the system, and since the system is closed, we can write the energy balance equation for the system. E in minus E out is equal to delta E, the change in energy of the system. The contributions in are due to the heat only, so that's Q in, and this is responsible for a change in internal energy of the system, delta U. So we can write this as M, the mass of nitrogen, times the specific heat, multiplied by a change in the temperature, T2 minus T1, the temperature of state 2 minus the temperature of state 1. Now, since no work is done, since the vessel is rigid, no work is done in the system. So the boundary work, W, is 0. Also, the specific volume is constant during the process, so we can find the final temperature from the ideal gas equation as follows. The final temperature, T2, since the volume is constant, is T1 into P2 over P1. So we can substitute our values in here. So the initial temperature is 298 Kelvin, multiplied by P2, which is 300 kilopascals, the pressure of state 2, over P1, which is 100 kilopascals. And so we get a final temperature, T2, of 894 Kelvin. Now we can put this temperature back into the energy balance equation and divide the energy balance equation by M to get the specific heat transfer, Q in, to be CV into T2 minus T1. And so we can find this heat transfer. So that's 0.743 kilojoule per kg Kelvin times the change in temperature of 894 minus 298 Kelvin. And so we get the heat transfer in kilojoules per kg to be 442.8